Okay, so throttling valves. Just get right to here. Throttling valves are just some sort of valve, and we do a control volume before and after. Okay? It could be this kind of valve, or it could be like a plug with holes in it. That's what the porous kind of plug is. All right? You see a lot of these, right? You want to close the valve, open it. But they're also actually pretty cool because you could change it and change enthalpy, which really changes temperature, right? Because enthalpy is a function of temperature too. So if we pick our point here as 1 and 2, is there any, we're gonna basically assume right now there's no heat transfer. Is there any mechanical object doing work? No. The velocities are the same here because it's the same size pipe. And we neglect the elevation changes. So we end up getting H1 equals H2. All right, so let's talk about heat exchangers. All right. Okay, so here's heat exchangers. All right, and here you have just like a box where you have flow coming in and flow going out, and then you have a cylinder in the inside, and you have flow going from your right to left. This is two different types of fluids, and they just exchange heat. Okay. And there's a couple ways we can look at this. And I'm going to go to the next slide, which has the same sketch. Okay. So if we pick the control volume is surrounding both fluids, A and B, okay, the heat transfer goes in one and out the other, so really the net is 0. Okay. That's if we pick both of them. In this object or this system, there's no mechanical work. The change in your kinetic and potentials are, we're going to assume 0 for just this case. And we end up getting, writing the first law, and when we cancel stuff, we end up getting this. Okay? So, but this is only the control volume of both A and B. What else are we assuming around this system? That it's not losing any heat to the surroundings, right? Because this is just the heat exchanger, not the surrounding. I think one of your homework problems, there's a case where it's losing heat to one, but then it's losing some heat to the surroundings. Okay. So down here, how many, in this case, how many are coming in both systems combined? Two, right? One for fluid A that comes into the control volume, and one that comes in for fluid B into the control volume, which is our dotted section. So each term, because there's 2 out, is going to have 2 terms, right? So you're looking at the overall system. Anybody have questions with this setup? Make sense? What do you think the next setup is going to be? Same control, same system, but if you want to know how much heat transfer is either being lost or gained, what do you need to do?
Make it only fluid A.
Exactly. Or you can make it fluid B. Yep. Let's just look at fluid A. In that case, there is no mechanical work. The change in potential, if we pick points 1 and 2 at the same horizontal, they're gone. And because this is the same size pipe, the velocities are the same, so there's no change in kinetic. So here we're looking at the heat transfer into or out of A from to or out of B, okay? So this time you're going to have a Q, okay? That's your heat transfer. Questions on this? What do you have to just kind of identify for Q? You have to know, okay, is it coming in or is it going out? All right. If you don't know, just make it Q, right? If you get negative, that means it's going out. If it's positive, it's coming in, okay? This is a pipe and duct flow. This is kind of like a mixing combination. You have a fan that blows air that way. You have heating, you have like a heating element. So in this case, you got Q, you have mechanical work, you have a whole bunch of stuff coming in, going out, okay? So there's going to be some cases where you have to have everything, right? It just makes it a lot longer. Okay? But you still write the first law, identify what's coming in and what's going out, label your points, figure pressure, temperature, enthalpy, specific volume. What else is there? What can you find in the back? Enthalpy, specific volume, temperature, pressure. I think there's one more. Yeah, internal energy. Okay. Next week on Wednesday, I'll show you entropy. You could find S. All right. So there's going to be one problem on this. I think there's a computer fan that's operating. It's sucking air in and then blowing it through the electronics. And I think it wants you to find a heat transfer. Okay, if I recall. All right. So I think there's one or two heat exchangers. There's a mixing chamber. And really, I'll go to the next slide here in a second, which is to summarize everything. You could have every component in a system, right? You could have nozzle, you could have a turbine, you can have a heat exchanger, mixing, whatever, okay? So in the end, and we won't do one of these, we'll get to a cycle, but like this problem right here is crazy, right? You can still assume steady state. We have water coming in. It's at certain temperature. This water in the tank is a new temperature. It's heat exchanger. There's mechanical work. There's stuff going out. Okay? You could actually run these calculations on that type of system, or here's a different one. This one's actually a unsteady one where you open this valve up. This is a throttling valve. It's just a valve that shuts on and off. And it shoots air into this, pushes this out this way with a spring. What kind of work do you have if the piston cylinder expands? Boundary work. Okay. See how you can use everything we've been doing now to apply to these types of problems. Okay. All right. I know a couple of capstone groups, they're doing some stuff with compressed air, which is like a cycle, right? And it's basically thermal. Okay. Who else is in capstone? What are you working on?
I'm working with Dr. Canadian on.
Oh, the robotic stuff?
Yeah.
Okay. So there's probably a little bit of thermal in there, some aspect of it. But hopefully you get the idea that we've done these separately, but you can combine them to systems.
Mm-hmm.
Before we look at cycles, we need to learn about the second law of thermo, which we'll start next week. Okay, that talks about general ideas of cycles. It talks about an ideal Carnot cycle, and then we'll move from there, okay? But as long as you understand, really what you have to do is write this, right? What's the other equation you need to write? That's what this is. Conservation of mass. If you write those two down in any problem, you can pretty much do the whole problem, right? Because you can identify where you are, what states. If you're a gas or a liquid or a mixture, you've already done that for the last 5-6 weeks, right? Figuring out what those are. So, okay, so let's go ahead and do this practice problem. Here we have a thin wall double pipe counterflow heat exchanger. Is used to cool oil. So we have a CP of the oil from 150 to 40 degrees at a rate of 2 kilograms per second by water. And we have that CP. That enters at 22 degrees C and a rate of 1.5 kilograms per second. Determine the rate of heat transfer in the heat exchanger and the exit temperature. All right, let's write some givens right here. 22 degrees C. M dot of the 1 H2O is 1.5 kilograms per second. Okay. T1 of the oil, 150 degrees C. T2 of the oil. So students have taken heat transfer. This should kind of look familiar. You probably did one of these problems. Cp of H2O, 4.18 kilojoules per kilogram degrees C. Cp of the oil, 2.2 kilojoules per kilogram degrees C. We're looking for T2H2O and Q dot. Assumptions. Got steady state. Q dot out of the oil equals Q dot in of the H2O for this particular problem. 3, and we'll pick uniform velocity. And what I'm going to do is, sure, I'll just redraw it here. Let's make a sketch. We're going to make oil our system. I was using purple. We're doing the oil because we don't know the exit temperature of the water. So so if that's, anytime you see that, do the control volume of the other one to find Q, because then you can use that Q to figure out the exit temperature. Okay, that's just a standard procedure once you get familiar with these. I called this state 1. This is energy of the fluid in. Here's the energy of the fluid out. And then we have Q dot out, right? Which is really Q dot in the water.
Yep.
And label this state 2. So, remind you, so I'll probably test you on this. Make sure you always label points and states, boundary, which is your control volume, and energies, okay? That's an easy problem for me to do on a test. And then now we go to the solution. And what are we going to write down? First law. Dynamics students, you could also do this, right? But you would cancel a whole bunch of stuff because we're assuming constant. You only have KE and PE of the system. Steady state means the energy in that control volume is going to stay the same. And I'm going to write it as Q dot in minus Q dot out plus W dot net plus the summation of M dot H plus V1 squared over 2 plus GZ. And this is N minus summation of M dot H V squared over 2 GZ, and this is out. There's a few things we can cancel, right? Q in, W net, and we're going to neglect, it doesn't give you any height changes, right? And it doesn't give you the sizes of the pipes. Okay, so the velocity in those pipes in and out, we'll assume the same. So we end up getting 0 equals negative Q dot out plus M dot 1 H1 minus M dot 2 H2. At steady state, we know that conservation of mass, M dot in equals M dot out. Oops. We know that m dot 1 equals m dot 2, and we'll just call it m dot of the oil. And so now I'll rearrange it. Q dot out equals m dot H1 minus H2. Yep, it does, yep. So you could, if you had a table of oil, go look those values up for H, right? But we don't. But you can actually switch this to CP T1 minus T2. So gases and liquids you can do that with, but not mixtures, okay? So oil is always going to be liquid from 1 to 2. So you can actually now switch it to CP delta T, just like we did for gases, okay? And I think we can find it now, right? 2 kilograms per second times, that was 2.2 kilojoules per kilogram degree C times 1,000, right? No. 1 kilojoule, yeah. Times T1, 150 degrees C minus 40 degrees C. Q dot out becomes 484 kilowatts. Yep, we haven't done that yet. We just found Q. Okay. Now, typically, experiments, they wanted to validate this. You would actually find the temperatures at all 4 locations, okay, and then figure out how to find Q theoretically like this, okay. So say now we want to find the exit temperature. Well, we need to do a control volume on the water. And which way is that going? Going in here. We'll label it 1, 2. Energy of the fluid in, energy of the fluid out. And I think this time we have Qn. So you got the first law, you got conservation of mass. And just to save some time, we end up with 0 equals Q dot N plus M dot CP delta T. And Qn is also equal to Q out. So I rearrange this equation and solve for T2, which is negative Q dot out over M dot of the water times CP minus T1. All right, we have this. We can now solve for this. So, why did I have?
Yeah.
Oh, sorry. There should have been a negative there.
Yeah. But they also be positive.
Yeah, I was going to say, why do I have positive? I missed that. Thank you. Yep, everything, all the negatives will go away. (99 degrees C). It should be higher than T1, I hope, right? Because we're adding heat.
Or higher by 7